Bye. This is Larry. This is day 11th of the June daily Leetcode challenge. Let's get right to it. Hit the like button, hit the subscribe button. Let me know what you think. Sort colors. Is it the one with 3 colors? Yeah, okay. Sort colors. Given an array with n objects colored red, white, or blue, sort them in place so that the objects of the same colors are adjacent with the colors in the order red, white, and blue. Oh, yeah. Go America / other flags. Here, I mean, I say other flags, but there's actually a well-known algorithm for this. Here, we will use the integers 0, 1, and 2 to represent the colors, whatever. You're not supposed to use the library sort function, of course. A rather straightforward solution is 2 pass. Yeah, that's what I was going to do, so maybe I won't do that. First, iterate the counting the 0, well, could we come up with 1 pass? This is kind of disingenuous, maybe. Like, if you ever get the... if you get this problem, if you ever get this problem on an interview, then like, you're probably not gonna come up with this, or maybe you will just from experience. But like, if you've never solved similar problems, it's gonna be really tough. The short answer is that this is a famous problem, and the colors are actually the Dutch colors. The Dutch flag colors. I know I made a joke about it being American, and I mean there are a lot of flags with these 3 colors, but the short answer is the Dutch flag problem. And actually, to be honest, I didn't know this algorithm for a long time, so I don't think it's really that necessary for interviews. And the counting sort I think would probably be okay if you ask me, but but I think I'm just going to take this out and. I was going to say I'm going to take this opportunity to do the Dutch flag algorithm, but that said, I think just doing it with counting sort is probably okay. And very rarely do you need this per se. And again, this algorithm I believe is Dijkstra came up with it, and I only bring that up not to name drop knowledge, but I bring it up because there are a lot of these problems where these algorithms are named after someone really famous, or maybe another way to think about it is that these famous people became famous because they came up with these algorithms, which is also to say, if you've never seen this before and you have 45 minutes to solve this problem, I don't think it's not reasonable to come up with this in 45 minutes when people are probably writing papers and maybe not their full PhD, but like on their way to get PhD with these kind of papers, right? So like, don't feel so bad if you don't get in 45 minutes during an interview, and or even during practice, so that maybe you do it later. But this one is a little bit famous, but not really. I didn't know it for a long time, so I don't feel that bad about it. But that's just my disclaimer. If you're still watching, because I don't know, you're not Googling Dutch flag algorithm, that's okay. But the idea is, this comes up a little bit for sorting algorithms in general, which is why it's kind of helpful, but it's still, But the idea is that, let me think about how to put it. But basically, the idea is just partitioning it into 3 different parts of 2 different places. And to be honest, I don't really have a great explanation of this. That's why I'm struggling a little bit, in that it's been a while. I don't think I've touched this in years. And I struggle to remember the core concepts to come up with from first principles. So again, some of that may be an excuse, but it's just I'm trying to. The point is that if you have issues with this, it's okay. Just practice and it'll be okay. But the idea is that it's kind of the way I think about it is kind of a variation of the 3 pointers or 3 pointers, 2 pointers algorithm, but with 3 pointers. So you could think about. Let's just put this. So the way that I think about it is that, let's say you have this array. Let's just make this longer for oops, something like that, right? And they don't have to have equal numbers of zeros and ones. But the idea is having, 3 pointers, one up here, pointer one, another pointer on the first one, and then the third pointer is all the way at the end. And the idea is similar to how you would think about a 2-pointer algorithm, but where you try to move things as you kind of see and process things. But the idea is that the last pointer is all things after this pointer are 2s. The first pointer is all things before this, or to the left. To the left are 0s. Let's just convert this to the right. And then here is just the second pointer is the middle pointer, if you want to call it that, where this separates 0s and 1s. Sorry, 1s and 2s. So in effect, what this does is that as they move around, the first pointer, you could kind of think about the first pointer as everything to the left of it is 0. Then the second pointer, everything to the left of it is 1, up until the first point, of course. And then the third pointer is everything to the left of it is everything to the right of it is 2s. And then you kind of keep on jiggling, moving your pointers in that way to keep the partition true. And and you probably hear we try to explain this a lot. You'll hear me talk a lot about algorithms in general with respect to invariance and what does invariance mean. And in this case, that's the invariant, right? Where, sometimes it's loop invariance, but sometimes it's just general invariant. But in this case, it is a loop invariant where after you process every number, these 3 things will always be true, or will still be true. And then if you're able to keep them true after every iteration, then at the end of the day, you have an algorithm. And then we'll talk about complexity at the very end, because then we have code to kind of go over. But the idea is that, well, you have 3 pointers, is the space complexity, which I guess is straightforward, and this time complexity, well, you only look at each number once, so that's going to be O of n, or linear. And I do a very hand-wavy first complexity analysis first, because I want to be able to be like, okay, because this is linear, then let's implement it because it'll be fast enough. So that's the idea. Because let's say we come up with a different algorithm and it's n cubed, and you're like, well, I don't know if I should implement it. Should I come up with a fast algorithm, right? So that's why I do it that way. And that philosophy comes in more handy with dynamic programming, as I've seen people just implement stuff without analyzing the dimensions. But that's kind of how I would think about it. Okay, so now let's get started then. Let's call these. For me, I'm just calling them left pointer, middle pointer, and 0 pointer. Pointer is equal to 0. Center or middle pointer is equal to 0. Right pointer is equal to n. So also let's define n. And we don't need this comment, so yeah. And then now we can just do for num in nums. And this is just implementation detail and thinking through whether I need the index and stuff like that. There are different ways to write this for sure, so definitely experiment with what you feel is the most comfortable. Yeah, so now for each number that we're processing, now we need the index because we need to do some swapping, I think, probably. So, or at least it'll make our life easier without keeping track of it as much. Okay, so now if num is equal to 0, what does a 0 mean, right? Well, a 0, if we get a 0, that means we want to put it where the left pointer is, and then we move the left pointer and the middle pointer. Yeah, right? And I'm coming, to be honest, I am coming up with this, like what you're saying now is how I'm thinking about it. I'm not looking anything up. And the reason, why I'm just thinking about it is, okay, let's say we want these two things to be true, or these three things really, right? What happens when we see a zero, right? Well, when we see a zero, we want to move that to the front. And then when that happens, we want to move this to the left and this to the, to the right, and this also to the right, right? So that's how I think about it. And this thing doesn't have to change because it only keeps track of the stuff to the right. Okay, so then let's do. Do I have to swap? I forget how exactly the details. That's why I'm struggling a little bit, but that's okay. Uh, let's see. Well, this in this case it'll be two. So is there in wherein about the in placeness? So another thing that I would say is that me personally, don't practice enough in place algorithms because in a lot of cases it's not necessary in terms of in terms of competitive programming. And interviews is a little bit iffy. I think in this case, it makes sense for it to be an in-place algorithm because it's sorting. So it is intentional that you want to manipulate the input array because in sorting you don't want to allocate all random space. But in a lot of cases, they're like more really constructed to be in place. So I don't know. But this one, I think it makes sense. But okay, so let's say this is 2. Yeah, I think this is okay because we never for going to left to right. Because so the thing that I worry about with swapping, and that's what I'm thinking through, is that if we swap something in, then like we lose. In this case, we lose the 2, right? But actually, that's not true because we process from left to right. There is some invariant in which, but if there's a number that basically we always move from left to right on. If you count this as a third pointer, an iteration pointer, we always move this from left to right one step no matter what. And here on both these two things, we may move it one step. We don't always move it one step, but we may move it one step, right? So in this case, these 2 pointers will never catch up to this pointer. So yeah, so okay. So now 0 to 2. And also I want to say that I'm not 100% sure about the middle pointer yet, so we'll have to think about it in a sec. Left pointer is equal to 0, and then left pointer increment 1, middle pointer increment by 1. Now let's do the other easy one first, where if num is equal to 2, then num sub right pointer minus 1 is equal to 2, right pointer minus equal to 1. So here, because we choose by n, so maybe we just do by n minus 1 so we don't have to do that way. So these are the second one should also be straightforward in that if we see a 2, we just put in the back. But in this case, we do overwrite stuff, so we have to think about it a little bit. Because what we said about the invariant going from left to right is no longer true here. So then now we have to think about how to take care of this thing. Yeah, the thing is that let's say we start with 0 here, right? And our current pointer is 2, then we want to write this to 2. But then that would mean that, well, that we lost some information, right? So, how do we take care of it? Well, in that case, can we just swap them? Can we just... Okay, I think what I think this is making it a little bit confusing for me because this pointer, as we said, move forwards no matter what. But I think what I now want to pivot or change a little bit is to let's go through the array in a more helpful way by using swaps. I was trying to come up with a way to see if I could do it without swaps, but it seems like here that's not the case. So And what I would think about doing is that, okay, like another way for me to think about this is, let's say this is 0, let's say we have 2. So then we have to replace this with 2, and then there's 0, right? And then now we have to process 0. And then now, well, let's just, or maybe this is a 1, right? So then we have to think about how to process that. So in that case, in that way, we just swap this here to the front and then redo that index. And I think that's a better way versus the way that I'm doing now, because here, it, for better or for worse, it always moves forward. So yeah, okay, so let's do that instead. Let's just do while middle pointer is less than n. Or I think we could even do better, right? We could do if middle pointer is less than right pointer. May have to double check they're off by 1. But because if they're at the same place, are we done? Yeah, I guess we're done. So, okay. Well, then let's do num is equal to nums of middle pointer. If it's 0, then this is true. And okay, let me just rethink about this for a second. And the question is, well, is this always true now? I mean, it kind of is always true, but we can actually write it more slickly so that we don't have to worry about weird cases. So how I would think about it is just do a swap from left pointer to middle pointer. And I'll explain this in a second. Let me finish typing it. Well, I'll explain a few things. But basically what this is saying is if this is 0, we swap it with where the middle pointer is. Oh, well, actually, well, now we don't have this, or this second pointer is the same as this pointer. So this is middle pointer. So let's say we are here, and left pointer, everything to the left of it is 0. So in this case, it'll be here. So let's just say there's a, yeah, let's just say there's a 1, because it has to be 1, and then now your middle point is here. And then now what do we want to do? Well, it's okay to swap this with this. In theory, we want to set the left pointer to 1, but we also care what it used to be, right? So in this case, we could just swap and then process this this array element again. So then we, yeah, okay, that's actually, this would be good enough. And this is just the swap syntax in Python, because there's some magic, but it basically sets the left of this tuple to the left of this input and right to the right, so it just swaps. And in this case, we can also do a similar logic where nums of right pointer, nums of middle pointer, and then we swap them. And then now, if they're equal, this means nums is equal to 1, then that means that this number is done and we could just increment. Is that good enough? It's been a while. So I'm not as confident as I would be. That's why practice buys you confidence, is when you've done it enough times. You're like, oh yeah, you just do this. And then, oh, I have to do, that's why. I have to do left pointer, increment by 1 in this case. And also you have to move the middle pointer. This is stuff that we talked about before. And right pointer, you subtract 1, as we talked about. Otherwise, this is middle pointer plus 1, because if it's just 1, you can swap it with itself, kind of. And I think that's roughly it. Though I guess I put this as a test case input as well. Is that right? No, there's an off by 1, as we had worry about. So I think this has to be equal to then. Yep. Okay. Am I happy enough with this? Yeah, that's this. I mean, I guess let's try empty array, one element arrays, and then, okay, so I'm happy enough. Let's go, YOLO. Cool. Yeah, so again, the way that I learn algorithms is just thinking about or remembering the invariants, and then everything else you could prove to yourself a little bit as you come along the way. It is still really tricky. I'm not gonna lie, but as you can see, how I kind of prove quote unquote everything from scratch. Let's go over the complexity a little bit. So this is O of n because middle pointer at most goes through all the elements. So there's only the number of elements. Each element will only be looked at once because every element can only be in the middle pointer once. And the space, well, the space is in place, and we just use 3 pointers, so that's okay. So it's all of 1. In terms of, yeah, in the real, I don't know. I've heard that this comes up from time to time, so I'm not sure, but I personally never seen it or seen my colleagues give it. But it's still an interesting algorithm. It's almost like I described earlier. I think of it like 2 pointers algorithm, except for its 3 pointers, and you have to kind of use swap. It's a little bit trivia-y in that, like, if you know it specifically, then it's okay. It's almost like a Fisher-Yates kind of thing where you do a swap with an in-place variable and kind of move them one by one, but it's a little bit different. I don't know. But yeah, for comparative programming, I haven't seen this at all. That's why I'm not familiar with this, because I would just use the library sort. It's slower, but it's not slower by enough that you would care that much. Generally, I mean, in the cases that might, it's a 1 in whatever case, and the big thing to know that it is 3 colors, so that's where it works out. And also, at a certain point for competitive programming, you just have to know it enough to know that, like, hey, if you see this algorithm, Google it. And then just to give yourself a refresher so you don't have to remember everything. I'm sure the really good people do remember everything, but I feel like that's not a good use of my time because I'd rather be better at, practicing binary search or something like this, right? Where it's like way more practical and comes up way more often. Anyway, that's what I have for this problem. I think, let me know what you think. Let me know how you solve this. Yeah, hit the like button, hit the subscribe button, and I'll see y'all tomorrow.